A deep dive into sklearn's experimental enable-iterative imputer. The enable-iterative imputer function in scikit-learn sklearn is a crucial component for handling missing values in datasets. It acts as a bridge between the traditional iterative imputer and a potentially more efficient but experimental approach to handling missing data. Let's break down the key aspects of this function. 1. What is it? Enable-iterative imputer is a function that activates an experimental implementation of a iterative imputer. This means it offers a potentially faster and more resource-efficient method to impute missing values. 2. Why experimental? This approach is categorized as experimental due to the following reasons. Potential instability: the underlying implementation is under development and might not be fully optimized or stable. Incomplete feature set: the experimental version may not have all the features or options found in the standard iterative imputer. Limited testing: it has not undergone the same level of rigorous testing as the stable version, so there could be potential unforeseen issues. 3. How does it work? The experimental iterative imputer utilizes a different internal mechanism to impute missing values compared to the standard version. It leverages techniques like parallelism. The imputation process might be parallelized across multiple CPU cores, potentially speeding up calculations. Optimized data structures: it could employ specialized data structures to improve the efficiency of calculations. Early stopping: the imputation process might include early stopping criteria to terminate calculations when sufficient convergence is achieved. 4. Key considerations: stability and reliability. Use with caution, as the experimental version might be less reliable than the standard iterative imputer. Limited documentation: due to its experimental nature, documentation might be sparse or incomplete. Performance variability: performance gains may vary significantly depending on the dataset and computing environment. Potential for breaking changes: the experimental implementation could change significantly in future versions. 5. Usage example: Python. From sklearn, experimental import enable iterative imputer. From sklearn, impute import iterative imputer. From sklearn, linear model import Bayesian ridge. Create an iterative imputer using the experimental implementation. Imputer iterative imputer estimator Bayesian ridge. Random state 0. Sample posterior true. Initial strategy mean. Maxiter 10. Toll 1 E-3. Verbose 2. Imputation order ascending. Use the imputer to fill missing values in your dataset. Imputed data imputer. Fit transform data. 6. Choosing between experimental and standard implementations. Standard iterative imputer use for production-ready applications where reliability and stability are paramount. Experimental iterative imputer consider for scenarios where you need potential performance gains, are willing to accept a higher risk of instability, are familiar with handling experimental features. 7. Future implications. As the experimental implementation matures, it could become a standard feature in future sklearn releases, offering a more efficient approach to imputation. However, it's essential to track the development progress and weigh the potential benefits against the inherent risks. In summary, enable iterative imputer opens the door to a potentially faster and more efficient way to handle missing values in your datasets. However, it's vital to use it with caution, recognizing its experimental nature and potential limitations.